EKG of the week. We're back with another EKG to run through and look at some interesting stuff. This one is a bit of a head scratcher, and this is one that you don't maybe see, or maybe you see it more often than you kind of realize, but you certainly don't think about very often. So let's take a look at this EKG. This is a pre-hospital EKG. Take a peek here and pause the video, see what you think. And I've gone ahead and left on the computer annotations just for the fun of it. See what you think, and start the video again when you have come up with an interpretation. All right, hopefully that's given you enough time. Let's look at this EKG. So we always start rate. What is the rate here? Looking across the bottom again, this is a 10-second strip. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 6 is, 70, 72? And computer says 71 at the top, so that's pretty darn close. How about rhythm? We look here, and across the more bottom strip, we see P wave before each QRS. They're not particularly prominent here, but you can make out a little P wave there. They look like they're all basically the same distance from the QRS. They all look more or less the same. There's a P wave before each QRS and QRS that follows each P wave. So we will call this sinus rhythm. So rate, rhythm, axis. And again, I usually poo-poo axis when I look at these things because it's rarely helpful. But on this one, we're going to do it, and it's actually going to show us something interesting. So looking at axis, I usually look at 1, 2, and AVF. So usually you expect lead 1 to be upright, and in this case, it is negative. So the QRS complex is mostly negative, mostly below that baseline. In lead 2, it's mostly negative. And in lead AVF, it's mostly negative. Now, if you've done much EKG interpretation or really thought about it or thought about an axis at all very much, you find out that that is a little bit abnormal. And actually, that's kind of a lot abnormal. So negative in 1, negative in 2, negative AVF. When we look at the old triangle here, to determine where axis actually lies at, we're again looking at lead 1, which goes like that from left to right, positive to negative, left, right, positive, negative, just like we think of. Lead AVF, which defines basically the up-down axis, positive to negative. So if the QRS is going towards the direction of the feet, it's going to be positive, i.e. if the electrical vector in the heart goes mostly towards patient's feet, it's going to be positive. And then lead 2, which is the other one I looked at, goes something like that, a little bit oblique. But when we combine those two things, we look at what we've got on the current EKG. So we said we are negative in essentially 1, 2, and AVF. So this green area over here is the area that is a normal axis. This area over here bordering that right, with that little yellow semicircle is right axis deviation. The red up here is left axis deviation. And then this area up here is where you just don't usually see a cardiac axis or an electrical axis, because that's the area if electricity was to travel that way, it would have to be going from essentially this part of the heart up in that direction. And electricity doesn't usually do that in the human heart. So let's look at where we are with this EKG. So we said we're negative in 1, which means this is the negative side of 1. The zero line is right here. So if it was positive, it'd be over here, but it's negative. So it has to be on this side of the circle. And that's already somewhat abnormal. When we look at lead AVF, it's negative in lead AVF. So positive AVF is down here, negative AVF is up here. And again, this is the center, the 0. So it has to be on this part. So already just looking at lead 1 and lead AVF, since the QRS is mostly negative in both of those, we know that it has to sit essentially up in this weird area up here where you don't really see a cardiac electrical axis, generally speaking. We notice we're also negative in 2, which means, again, here's 2 sits right here, and the 0 line is essentially this one that it runs along AVL. So it has to be up here someplace on this side. So it has to be over here based on 1, has to be up here based on AVF, and it has to be over here based on lead 2, which means the only place it really can be is right up here in this area of extreme axis deviation or no man's land. And again, you just don't usually see that in a beating human heart. That's just not something that usually happens, because it means that the primary direction of electrical force is going that way, going from kind of patient's bottom left up to patient's upper right, kind of the opposite way that you usually expect electrical current to flow through the heart. As I mentioned, this is kind of an odd thing, and there's really kind of two ways that happens. One is that you've just infarcted a ton of tissue in your heart and created all those Q waves, but the other thing that happens is that you put the leads on the patient wrong, and that, in fact, is what I believe happened here. In fact, I'm 99% sure of it. If it is completely backwards, we got to think, man, the first thing you got to be thinking is, did we make an error when we applied the leads? And why would we think that? Well, here's what you get when you put on the limb leads on a patient. You have the right here, or the white here on the patient's right. You have the black one on the left, and then you have the red one on the left foot or left ankle. And then you usually, you have a ground or neutral in here someplace, that green one. So, and doing that generates the leads that you kind of see. So lead 1 goes like that. Lead 2 measures the difference between voltage here and here. Lead 3 measures the difference between here and here, etc. The AV leads go essentially center of the body down to the foot. So AVF goes that direction, or down to the lead. So here's kind of center down to the foot. Here is kind of center of the body up to the left arm to that lead, and AVR goes from the center of the body up to that one. Now, say that we take the white and the black lead and we switch them. And then we do that would change them on all the different leads as the computer interprets them. What we now have is essentially you reverse the direction of current for lead 1 so that it goes like that. Lead 2, since the leads themselves are just reversed, that would make the axis look more like that. So it kind of flips over. And lead 3 looks something like that. And you notice when you do that what you see in lead 2 looks a lot like lead 3. So there's what you subsequently get in lead 2, and it looks a lot like what lead 3 should look like. Likewise, lead 3 looks like what lead 2 should look like. So when you get these things, you notice lead 1 switches, it reverses direction. So what is negative should be positive on the misplaced EKG if you misplace the limb leads. And then lead 2 and 3 ought to switch directions. Likewise, AVL and AVF ought to do kind of a similar thing. They ought to switch places. So AVL on the new EKG is going to be going like that, and lead AVF is going to be going like that. And AVF, AVR here looks like the way AVL usually looks like, and AVL here looks like the way that AVR used to look like. And by the way, AVF, because it only goes from the center of the body down to the foot, and you didn't mess up the foot placement, you didn't change the foot placement, that stays the same. So what do we get? In summary, if you were to take the two upper extremity leads, the lead 1 and lead 2, essentially, what you would find is that the lead 1 becomes upside down. It reverses. So what would have been positive on the tracing now is negative. Lead 2 and 3 switch places. So 2 becomes 3 and 3 becomes 2. And AVL and AVR switch places. AVL becomes AVR, AVR becomes AVL. Does that look like what we see on this EKG? Just to prove it. And by the way, why is that kind of noticeable on here? Because when we look at this EKG, this top portion is the EKG that was transmitted in. This bottom portion is the EKG after we saw the patient in the emergency department, made sure the limb leads were replaced in the right way, and reran an EKG. Is that what it looks like happened? So again, what happens? Lead 1, which again, this is the old one. So lead 1 should flip. Does it flip? Yes, it's that same kind of morphology, but now it's upright instead of down. Lead 2 and lead 3 ought to switch places. So lead 2 should actually look like lead 3, which it does. It's got that little ME thing down at the bottom. It's mostly negative, and that looks mostly like that. And again, account for differences in machines, that kind of stuff. And does the morphology of lead 3 in that one look like lead 2 on this one? Yes, it does. You've got that little tiny R wave and then a mostly negative Q with the little funky stuff down at the bottom, or not Q, S wave. Yes, that does look pretty much the same. So that looks like that. Just to confirm, AVL and AVF, AVL and AVR should switch. AVF should stay the same. AVF does look mostly the same, all told, again, just accounting for differences in machines. And then AVL on one should look like AVR on the other. So AVL here should and does look a lot like AVR, and then AVL here should and does, being mostly positive with that little M thing at the top, look like AVR. So in this case, we've got a pretty good indication that this is a limb lead reversal, and that is likely what's causing kind of that funky axis. If you were to just look at this, not to skip ahead, but to skip ahead a little bit, if that wasn't the case, you would see there's a Q wave here, there's a Q wave here, there's not really a Q wave, but a funky looking complex, Q wave here, Q wave here. Those are all signs of old infarcts. You know, going across the precordial leads, you do see some ST changes that might be concerning as well. You get kind of poor R wave progression. But what this looks like, if it is done properly, if this was a properly done EKG and this is what it spat out, this would be somebody that you'd be concerned has had a lot of infarct, that has already gone through and developed and essentially, you know, queued out is what they say, been present for a long time. So this is either a huge multivessel infarct, or the leads were placed improperly. And in this case, it's the leads were placed improperly. We said rate 72, so that's normal. And by the way, this is a stable, super stable patient who doesn't look like they have infarcted their entire heart, essentially. Rhythm is sinus. Axis is way right. It's into that no man's land. Whenever you see that, your first thought ought to be, did I put the leads on right? Let me take them off, put them back on in the way that they're supposed to. And you find that will actually change a lot of times. All right, rate, rhythm, axis. How about the intervals? I'll tell you that you've got a wide QRS. That is true. If you remember, our QRS is going to be 3 little boxes or less to be normal. And it looks like from the start to the finish of it, it's 1, 2, little more than 3 there. Kind of look down here. 1, 2, little more than 3, almost getting to 4 little boxes by the time it's all over. So, we see a wide QRS. It looks a bit like a left bundle branch block, although V6 doesn't really seem like it. Certainly certainly the precordial leads do. But again, this might be a little bit influenced in terms of the morphology, because there is that limb lead reversal. So it's tough to call it a definite, fits a left bundle, fits a right bundle, that kind of stuff. Let's call this interventricular conduction delay, because it is a wide QRS, so something is clearly slowing it down, and it looks like it's sinus otherwise. Otherwise, looking at our PR interval, when we measure from here to here, again, we're measuring the start of the P wave to the start of the QRS complex, and that should be under 1 large box or 5 little boxes, and it looks like it is 1, 2, 3, 4. Certainly under 5 of them. So normal PR interval. And when we look at the QT interval, also looks essentially, at least to our eye, it looks like the QT, the difference or the space between one QRS complex and the next QRS complex, it looks like the T wave finishes before halfway through there. So that's a normal looking, at least grossly normal looking QT interval. All right, let's look at ischemia and infarcts. As I mentioned before, if you run through here, you would say ischemia and infarcts, why they're all over the place. First of all, just let your eye kind of gravitate to what it sees. Going through the precordial leads, not specifically elevated, not too bad here. This is the one that the crew was concerned about, because they saw there was this large bit of ST elevation here. Now, it's worth noting that in the setting of like a left bundle branch block, you will get ST elevation in the setting of an interventricular conduction delay, or something that gives you huge negative complexes, as you see here, that big deep S wave. That will cause you to get an ST change. And it usually goes, if the heart is going to work in the way that it's supposed to, that will go in the opposite direction. So if it's a big, huge negative complex, then the ST segment ought to go in the opposite direction. And so that is what you see here. That's check out our left bundle branch and right bundle branch block video to kind of explain that more. But that's a big negative QRS complex, and the ST segment's going in the other direction. Remember, you get some more space in V2 and V3 to have a bit more ST elevation as well. You do see a bit of ST elevation here, but I'm going to say that doesn't look like pathologic ST elevation so much as it does the change from the change based on that huge negative QRS complex. Same thing here. There is a little bit of ST elevation. It might reach a millimeter depending on where you measure it from, but I'm going to blame it on something else. And I'm going to say there's not clearly a pathologic here. Now, this one I would be concerned about. There's, as we kind of see here, easily 2-3 millimeters of ST elevation after that QRS complex. But again, that is going to end up being because the EKG was performed, that was obtained incorrectly, and so you'll see that. But it is based on that same principle. If you've got a huge negative QRS, then you're going to get some ST change in the opposite direction, and it's very hard to figure that out. So ischemia, infarcts, hard to tell. The one thing that, as I mentioned before, is a little bit weird is that there's all these Q waves. If it is and Q waves are a sign that you've already infarcted the heart, that the muscles died. If there's that much Q wave in there, then this should be a really, really sick heart. And clinically, this person ought to look pretty terrible. You see no R wave progression here either. In that setting, this ought to be a pretty extensive infarct, and you just don't see that clinically in the person that was awake, talking, essentially not complaining of anything at that point. So I'm going to say yes, absolutely be concerned for ST elevation if that EKG is properly obtained. But in this case, we'll find that essentially that all comes down to old changes and a combination of limb lead reversal, which can really screw you up. Yes, I would be concerned about this EKG if we're sure that it's properly obtained, but we could kind of tell from that weird axis to start with, as well as just kind of seeing a ton of these things, that this wasn't quite right to start off with. Pattern-wise, I'll just say that it meets those limb lead reversal patterns that we look like. If you've got a whole bunch of big negative complex in lead one, that usually ought to clue you in that something is off. That there may be a limb lead reversal. And by the way, the crew attempted to obtain additional EKGs, and they said, well, it looked the same each time, so we didn't think it was a mistake. I'm like, well, if you don't take the leads off and put them back on, then how would you ever know? Like, yeah, that just kind of proves the EKG machine is working and seeing the same thing each time. That's what it's supposed to do. So if you're concerned about it, take the leads off, disconnect the patient from it, start again and put them back on. Takes a couple of seconds more, but it can cause, this could have been a big change in the destination of this patient or the trajectory of this patient, all told. But it does have that limb lead reversal. So what are we going to give our overall impression to? We're going to call this a sinus rhythm with a way extreme right axis and concern for limb lead reversal. Overall, this looks like a really bad older infarct that's been going on for a long time, or user error. And in fact, we find this one to be essentially user error in the way that it was obtained. Now, we all do this. It's easy to switch those limb leads, and you've probably done it and not even noticed it before. But that just goes back to that same principle. If something looks funky, then take all the leads off, start again. It doesn't take that long to do, and it can make a big difference, especially if things just don't line up and don't make sense. All right, that is our EKG of the week. And by the way, when we looked at the regular or the properly obtained EKG, most of those changes went away, and it looked significantly less concerning. Anyway, that's it. So like us, follow us on the YouTubes, and check out emsgrandrounds.org for more educational videos. We will see you later.